All right. Hi, everyone. So my name is David Ballard. Okay. And today we will learn about machine learning, part of the Google Student Developer Club. Okay. So firstly, let me just get my notes here and we'll get started. Okay. So yeah, we're going to start off with what you need to know. So if I am asking you to write a program to see if someone's smiling, this is a very good first task to give a student um, to learn about computer vision, okay, and feature detection. So how would you go about doing that with your knowledge right now? Or if I asked you to predict the motion of a system by observing it, okay, how would you go about doing that? Well, let's talk about the first problem. So in the way you might think of it right now is, oh, let's try to make a program that could look at someone's features, like if their teeth are showing, or if they have crow's feet, the corner of their eyes when you smile, okay? Or if their corner of the mouth has marks, okay? When you smile, when you grin, okay? This might seem like a decent approach, uh, being tracking certain features and images or hard coding those features or extracting those features from images. However, this may seem unintuitive to code. And there's one main issue. Everyone smiles differently. Everyone's face is different. So how would you code a reliable solution to that problem? So so I'll just draw out those features quickly. So again, well, this is my poor rendition, but I was talking about when you're smiling, okay, you might have these marks here, okay? Or you might have these crow feet here, okay? Those are features that we could encapsulate when we're trying to code a program that might check if someone's smiling, okay? Again, it's difficult. This is the data portion of the problem, getting this data. But it is difficult because everyone's face is different. Okay. So this is why we might want to use machine learning, AI, certain model to solve that problem. Okay. So, and this also ties into an important point, the most important point, in fact, which is the data. Okay. I'll get there. All right. So perfect. You guys see the board? Okay, kind of. Okay, I hope it turns out all right. Okay, so um, okay, we'll continue. So where was I? Um, 1 second. So let's go on to the second problem I mentioned, depicting the motion of a system by observing it. Okay, so you may have learned in differential equations that there are certain models, there's certain equations that model certain systems that may seem like a good approach. However, often numerical methods, which you'll learn about if you take numerical methods, okay, like Runge-Kutta, using that to numerical integration, using that to solve the motion of a system. Again, if there are too many variables, or you cannot model a system reliably, like fluids, okay, it is difficult, okay. Yeah, many times these systems have too many variables, or you're not sure how they interact, or let's say we're trying to model a very complicated changing magnetic field, okay. um that is a problem that, if you do not know how to model it mathematically, you might not know how to solve that problem. Okay, so this is the reason why another approach must be considered. So if we had a general structure of a model that could do these tasks and we fed it data so the model could fit itself to that task. So what we're trying to do here is fit a n-dimensional function. Okay, calculus, you learned 3-dimensional up to n-dimensional curves. We're trying to fit this n-dimensional function, and this is the essence of machine learning. Why n-dimensional? I'll get there. It has to do with the input, the function. Okay. And with this, one can make predictions or decisions given a data set. Okay, so this sounds fantastic. Just give code some data and I'll spit out a prediction of exactly what you're looking for. Well, not exactly. All right. The problem and the task at hand still needs to be meticulously defined by an engineer in order to solve problems properly, or else your model won't have any idea how to fit the data provided to it. So yeah, we can't just have a nice data set. I'm gonna just throw it at a model and it'll solve my problem. You have to define the problem and explain that to the model. So that's really what I want you guys to get good at is how to structure a problem. Okay, the right thinking that goes behind it, not just coding. And I really want you guys to build that problem solving skill. Okay, so it's like if I showed an infant photos of different bird species or animals and I told them to classify them while giving them the names of the birds. The child wouldn't know what or how to classify it. So that's just giving data without giving labels to the data, for example, which is a specific type of data that we'll get into. Okay, so we could describe problems and their solutions using 6 characteristics, 3 of which characterize the problem and 3 of which characterize the solution. All right, so firstly, we have the problem class. Okay, hope you guys could see. Okay, we have the problem class. All right, so what is the nature of the training data and what type of queries will be made at testing time? Okay, next we have assumptions. Sorry, assumptions. Okay, what do we know about the source of the data or the form of the solution? Okay, then we have the evaluation criteria. Okay, so what is the goal of the prediction or estimation system? So what's the goal of our model? Okay, how will we answer to individual queries being evaluated, or how will the overall performance of the system be measured? Okay, so how are we evaluating? What assumptions are we making, and the type of problem? Okay, then we have here. Then we have the model. Oh, I have space. Okay, can you guys see here? 1 second. How far do we go? Yeah. Okay, we have room. 1 second. 1 second. So I'm recording because 3 people couldn't make it today, so they'll be watching from home. So here I'll do a little summary for Rootvid. She just came here. Okay, so basically what we went over is that I have a problem that I want to solve. Okay, let's say we have a computer vision problem. I want to see if you are smiling or someone is smiling. Okay, this if with your knowledge so far, forget anything you know about machine learning. If you want to figure out if somebody's smiling, you would try to look for certain features. Okay, you would try to look for if they have a grin. Okay, if their eyes have crow's feet, their teeth are showing. Problem is, everyone's face looks different. Everyone's smile is different. Okay, another problem. Okay, if we're trying to model a system, I was saying very complicated changing magnetic field. We might not have the equations to model that system. So going back to differential equations, we have basic equations for projectile motion, uh, and such and such. Okay, if we don't have, if one, our system's too complicated, or we don't have the equations to model that system being too complicated, like if we're dealing with fluids, or we can't use numerical integration techniques like Runge-Kutta. Okay, you'll learn about that when you take numerical methods. If we don't have that, then it's very hard to model our system. But the essence of machine learning is that we're trying to fit this function, this n-dimensional function. Okay, so yeah, we want to get a general structure of a model. Okay, and that could do these tasks. Yeah, that could do all these tasks, and we feed it data. The thing is that we can't just throw data at code or a model and expect it to give a meaningful prediction. We have to structure the problem. Okay, and that's the role of an engineer. Okay, so um, so we were going over what can describe problems and their solutions using 6 characteristics. Okay, so we have the problem class. Okay, the nature of the problem and the training data. We have assumptions, like what do we know about the data? What can we assume? Okay, we have our evaluation criteria. What is the goal of the model, of the prediction estimation system, whatever you want to call it? Okay, then we get into model type. Model type. Okay, this is big here. Okay, will an intermediate model be made? What aspects of the data will be modeled? How will the model make predictions? And we have model class. These two are very important. Okay, model class. Okay, what particular parameter class of modules will be used? What criterion will we pick to for our particular model class? Okay, so uh, architecture is extremely important. We cannot just pick any type of model for any type of problem. There has been, you need to go into it depends on the task. Okay, you have to go into specific research, new research on what people are studying, what type of models perform best under certain tasks. Right now, transformer based architectures are the rage. Okay, people are using them for LLM. Okay, they're using them for practically everything, computer vision. Okay, image detection. Okay, anything. The thing is, there are other architectures. Okay, we could have in basics, like we have linear, we got like we'll learn about like linear regression, but it's very basic. Okay, we have there's a specific, we'll get there much later. We have state space models. Okay, and that's, I'm going on a tangent, but we'll get to different architectures. But it's very important to choose the proper architecture, the proper model for the task. Okay, and we'll get into defining the criterion a bit later. Okay. Yeah. Yeah. So that Rudvich asked, how do you get the intuition? Okay. That comes with one, experience, two, research. Okay. You have to understand, often you need to understand the problem you're dealing with. Okay. So one second. So in my experience, it depends the task. Okay, you want to research what models are doing very well overall. Again, transformer-based architectures perform very well on many tasks. But to find the best model for a specific task, you have to consult often other researchers on they're benchmarking these models. Okay, they're doing overviews of studies on which models perform best. Okay, and it really depends because it's not just a question sometimes of what is the best model. It's what is the best for your problem. Okay, that gets into ML ops. Okay, machine learning operations. Okay, what model do you want to pick that is good for your solution? Okay, so it's not necessarily the best performing because you could have restrictions. Yeah, you have budget, you have money. Okay, you're working for a company or you're starting a company. You don't have the expenses to run again running these expensive models that are computationally expensive, hardware expensive. Okay, I know maybe you guys know some of this. We'll get into GPUs maybe next lecture. Okay, but you need a very powerful graphics card with a lot of video RAM. Okay, to do these matrix multiplications. Okay, which is the essence of what we're getting into. Okay, um, that's expensive. That costs electricity. It costs a lot of money. Okay, and you have to run it and you have to put it somewhere. And there's cloud computing. We'll get into that after. But regardless, it's expensive. So you may want a lighter weight model, and that's not a bad thing because on certain tasks, lighter weight models will perform better. It depends on your data. Okay, it depends on how much data you have. Sometimes a very big model will perform worse on small data compared to a smaller model because it'll overfit, overgeneralize. Okay, so and lastly, last criteria, we have algorithm. Okay, this is really this is what has to do with the problem, the data. This part has to do with the model. Okay, what computational process will be used to fit the model to the data and or make predictions. Okay, so let's get into data. Okay, so the most important thing, the things that, what do you need for a machine learning problem? Okay, what do you need? First thing, which is the most important, is data. Okay, you need often, you need as much as you can. Okay, depends the problem, but you need as much as you can. Okay, to get a reliable solution. Because let's say you're studying for a test. Okay, you're studying for a test, and I give you homework problems. Okay, I give you 10 questions, and then but you have an entire textbook to study from. Okay, you will not perform well. You will perform exceptionally well on those 10 types of problems I give you because you will study them over and over again. But then I show you the test and then you don't perform well. That if you're overtraining on small data and it doesn't generalize well to your test set, you will overfit. Okay? Okay, you will generalize. You won't generalize. Okay, you'll be too specific on your test set. Okay, or on your training set. Okay? So what do you need? You need as much as possible. Much as possible. Okay? But you don't want garbage either. Okay? You want quality data. Okay? Quality. Okay? So you want as much data as you can and you want quality. That's what makes a good solution, okay, to your problem. Okay, so the first part of the problem is collecting data. So let's say, we'll go back to the smile problem because it's easy to explain. Okay, let's say I want to check if someone's smiling. Okay, I will get photos, a lot of photos of one. Well, if we're doing binary classification, let's say. Okay, so we're doing binary classification. Okay, So if we're doing binary classification, we want to find a lot of photos and a lot of types of photos, different angles, different people, okay? Of people smiling and people not smiling, okay? And we'll have people smiling with their teeth, whatever we consider a smile, okay? And we will label these photos as 1 for smiling and 0 for not smiling, okay? So this is binary classification, okay? We'll have a photo as a vector of which we'll learn later, a tensor, okay? Depends the quality, it depends the image, but let's say we have a square image by 512 by 512, okay? That will correspond to a tensor of 512 by 512 by 3, okay? For RGB, okay? So matching dimensions, which will first, you have to turn this tensor into, sorry? Yeah, you'll have to turn this tensor, you'll have to rescale it into a integer, okay? You will have to get into a form that could be evaluated by your loss function, okay, which is dependent again on your loss function, okay? So you will have to rescale the dimensions. So dimension matching is very important for another lecture, okay? So matching dimensions. So we have here, just quickly, for if we're dealing with image processing, image recognition, okay? We have the size of the image, okay, as a tensor. So this is a vector where its dimension is 512 by 512 by 3 because we have red, green, blue, okay? That's just an example, okay? And we're dealing with binary classification. So quality of data is how we're labeling, okay? We want to label our data reliably. If you have a bunch of data and you're not labeling it properly, it's not reliable. You're not going to solve your problem. Okay. And you want as much as possible. Okay. That's the gist of it. So that's data. We'll get into types of data. Next thing, we talked about this. Okay. Next thing, I think I have room here on the board. Let me check. Just so for the people watching, can you guys see? Okay, you guys could see. Okay. So maybe I write in black. It'll be a bit better. Let's try this. That's okay. There we go. Okay. So model type. Okay. Model type. We talked about this. What type of model? Okay. What type of architecture? Okay. This is where you have to do research. Okay. There's no answer to what, especially if you're tackling a new problem, what type of model will be best. Okay. If you're doing cutting edge research and you have a new task that no one's ever done, you need to figure out what type of model works best. And then this kind of gets into merging models, okay? Okay. So if you're doing like an amalgamation of models. Yeah, kind of. So like if I don't know what model works, how can I figure out what model is best? You could do a bunch of educated guesses. You could do a bunch of hypotheses and find the right model class. Okay. So we'll get into that's later. Okay. So we have model type, we have data. Now, how are we going to split up our data? Okay. We have how to split data. Okay. Well, we first need, going back to the test analogy, okay, we first need to have training data. Okay, this is your homework problems. Okay, this is what you're going to be studying for your test. Okay, then we have testing data. This is the actual test. Okay, the thing is now when we're evaluating, okay, when we're evaluating our model, we want to train and then test as we're training, kind of. Okay. This is where validation, okay, comes into play. So what I could do is I could say I'm taking, let's say, 10% of my training my training data. Okay. And as I'm training, before I get to the test, as I'm studying, okay, as I'm studying for my exam, I'm gonna take 10% of my homework problems. I'll do a mock test, okay, and then I'll come back and train some more, and then do a mock test, and then I'm gonna see how I'm doing, and then I take the test, and I see how I do. Okay, that's kind of where we're getting at. Okay, so how to split the data. Okay, now, this is good. I hope you guys wrote this down from people watching at home. Okay, I mean, this part wasn't that important. It was a little bit of a tangent. Okay, so loss function. We'll get specific later. Okay, loss function. Okay, so every problem, I want to know how sad, how bad my prediction is. Okay, and that depends again on my problem. Okay, it's not a general case. It's not you're gonna have I mean, for binary classification, we'll go into or we'll go into different types of loss functions for more general problems, but for very specific problems, yeah, exactly. But for very specific problems, it depends how you're evaluating your loss. Okay, it depends what type of problem you're doing. Okay, so that's the loss function. Okay, so it's how bad or how sad am I that I made this prediction. Okay, how sad or how bad is my prediction? Okay, so let's continue. Okay, so we'll go over quickly just some notation. Sorry. Okay, just some notation. Okay, so we have our data set. Okay, what is a data set? Okay, well, for supervised learning, let's go over that. Supervised learning. Okay, we'll go over different types of learning now. Okay, in general though, my data set, d sub n, is going to be a set containing x, y pairs. Okay. 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 It's where x is my input, and y is my output. Okay, so that's my data set. As we said, for our image problem, okay, if our smile problem, our input is going to be images, but we have to process them. So we're going to turn them into tensors. How are we going to process the tensors? Well, if we want to normalize all our data, if we want to make all our data the same, there's certain types of transformations we could do beforehand. We could do a horizontal flip, we could crop, we could get it to be more normalized, our data. Yeah, we augment them. Yeah, exactly. Okay. So our data set is composed of question answer pairs. Okay. So our question for image recognition is, are we smiling? Our photo. Okay. Our answer, our output is 0 or 1. Yes or no. Okay. So xi as I mentioned, will be an n-dimensional vector tensor, and y could vary. For binary classification, 0, 1, we could have labels. We could have many. If we're sticking with images, yeah, we could have labels, binary classification, or we could be measuring on something else. Yeah, exactly. We could have a y could be a very large parameter. Okay, yeah, exactly. Yeah. So multiple labels. Yeah. Okay. So I went over that. Okay, 1 second. So now, we went over supervised learning. Okay. So unsupervised learning doesn't involve learning a function from inputs to outputs based on a set of input-output pairs. Okay, so it's a little different. Okay, instead, you're given data. You're given a data set and generally expressed to find some pattern, structure, some inherent pattern to the problem. Okay, so you're given. Here we go. Unsupervised. Uh, unsupervised. Okay. So we're given samples. Okay. X1, yeah. We're given our input. X1, X2, Xn. Okay. And which is an element of our dimension D. Okay. Okay. The goal is to find partitionings or clustering of a sample that groups together samples that are similar. Okay, there's many different objectives depending on the definition. Okay, so yeah, you're trying to find groupings. Okay, so or clusterings. Okay, and that's pretty much it. Okay, we'll stick with the supervised learning for now. And reinforcement learning we'll go over another time. Okay, so we have like 10 more minutes around. Okay, so let's go over our loss function. Let me get my notes. So we'll go our last. We covered quite a bit. I want you guys to understand and not have too much to study for our next session for the people watching at home. So let's go over. We went over the general structure of our problem, but let's go over our loss function. Okay. So our loss function is how bad is it? How bad did we make that prediction? Okay, so our output, ky, our prediction, we'll just call it prediction so you guys aren't confused, is a function, okay, of our hypothesis. Like that's our model. Okay, the output, our prediction is the output of our model. Okay, and we have our parameters. Okay, we have data. We'll call it data, but this is what we're inputting to our model. Okay, so we have x, our input, and a bunch of parameters. Okay, so now our loss function L, okay, this is our loss, is a function of G and A. I chose, or this is canonical depending on who you ask, but G is our guess and A is our actual. Okay, again, depends on what type of loss function we're using. Okay, if we're looking at 0, 1 loss. Okay, 0, 1 loss. Okay, we have our L of G of A if we're dealing with 0, 1 loss. will be mapped to 0 if G is A and 1 otherwise. Okay, so if our guess is what we want, we say it's 0. If it's not, we'll have 1. Okay, squared loss. Okay, squared loss. Okay, so our L of G of A is the difference between our guess and our actual. Okay, the thing is, if we're doing binary classification, okay, we just, our model will output 0 or 1. Squared loss is not great. Okay, 0 1 loss is better. Okay, so again, it depends on your problem. If your guess and actual, let's say, were decimal or decimal numbers, okay, from, let's say, 0 to 1. Okay, so guess is an element from 0 to 1, and actual is an element from 0 to 1. So we have all the decimals in between. Square loss is fine to use. Okay, so if we're looking now at square loss, we have here, we'll go here, linear loss. Okay, again, these are very general. Okay, if you're dealing with more specific problems, you're not going to be using these often. Okay, more complicated problems, you have a very specific loss depending on your problem that's designed for your problem. So you'll design the loss function. Okay, linear loss, the absolute value of the difference between your guess and actual. Okay, there's asymmetric loss, but we're not going to go over that. Okay, there's a bunch of loss functions, and again, it really depends on your problem. Okay, last thing we'll go over. Okay, so we have our loss. We now want to know, like, how bad. We have our loss here, but we want to know our error. Okay, we want to know over the entire training, how much loss did we, the average loss, okay? How much loss did we experience? Okay, so okay, training error. Does the camera see over here? Okay, last thing. And then maybe I'll get go wipe this down. Okay. Okay, so training, I'll write bigger. Training error. Okay, so my notes. Okay, so our error, call E, our error, so you guys understand. Okay, our error, which is our function of our hypothesis. Okay, or we put in our hypothesis as a parameter. Okay, we're going to sum. Okay, an average 1 over n. We're going to sum from 1, okay, to n. N is our training examples. Okay, we're going to sum all of our training examples from 1 to n of what? Our loss function. Okay,